Hi class, so today we are going to be covering the topics that you need for our lab on hearing. So today we're going to talk about consonance and dissonance, perceptual organization, and localization of sound. And so the first topic that we're going to cover is consonance and dissonance. Okay. So for consonance and dissonance, what we're really concerned with here is playing two tones at the same time. And more importantly, what happens when you play two tones at the same time. Okay. So essentially, if you play two tones at the same time and they sound really good together, we call that consonance. And if you play two tones and they sound really bad, that's dissonance. Okay. So the question then is, what causes two tones to sound good or bad together? And that is actually the critical bandwidth. Okay. So the critical bandwidth is defined as the difference the ear needs in frequency in order to hear two sounds. So when you're playing two sounds together, if you can distinguish the two sounds, it sounds good. If you can't, then it creates dissonance and it sounds bad. And so the critical bandwidth is the frequency that you need to determine and be able to hear the two sounds. And so it would look something like this. So here I have if I have two tones, A and B, and they fall outside of the critical bandwidth, then you would hear two tones, and that would sound okay. That would end in consonance. But if I have two tones, X and Y, and they're in this critical bandwidth, they're in this frequencies that are too close together, then you would hear one tone and it would cause dissonance. And so dissonance essentially is when two tones fall within the critical bandwidth, what you get is something called a beat. So if you remember from previous classes, we talked about how tones have frequencies. And so when you have two tones at once, what ends up happening is that the tones add the frequencies together. And if they're too close together, instead of being able to distinguish the frequencies, you end up with something like this. Where when you add the frequencies, rather than being able to tell them apart, they would go something along the lines of this. Right? And so what you can see is you have this increase in frequency, in amplitude, right? So remember, amplitude gives you loudness. So you have this increase in amplitude and then a decrease in amplitude, and an increase in amplitude and a decrease in amplitude. And that's what gives you the beats, is that when these are so close together, you're adding their frequencies, you have this oscillation, right? And so the beats are oscillations in frequency, right? And so because it's oscillating, it essentially changes the loudness. And you have a sound that kind of goes in and out of loudness. And it's very, very aversive. It turns out that when we play music, tonal music, the music that we use to compose songs or music, makes sure that two tones never fall within the critical bandwidth. So you never actually get dissonance in beats if you're playing to the rules of tonal music. And this is just a fun fact. In tonal music, there are 12 semitones that exist, and each culture creates a subset of tones. So for example, in Western music, we have 7 notes that comprise tonal music, and in Eastern music, it actually ends up being 5. And so we pull from this set of tones that never fall within the critical bandwidth to create music. Okay, so that's consonance and dissonance. So the second aspect of hearing that we're going to talk about today is perceptual organization. And so if you remember when we talked about vision, perceptual organization is really about how we put our perception of objects together. So in hearing, perceptual organization is about how we group the notes that we hear together. And so if you remember in perceptual organization, we spent a lot of time in vision talking about Gestalt psychology. And if you remember again, one of the principles of organization in Gestalt psychology for vision was grouping. And it turns out that that same principle is actually very important for hearing. And so in hearing, when we talk about perceptual organization, we're really concerned with how we group objects together. And so that really falls out into two aspects of perception. One is pitch streaming and the other is pitch segregation. Okay, so first let's talk about pitch streaming. And so pitch streaming, of course, is again how we put musical notes and sounds together. And it turns out that sounds that are close together in both pitch and time are grouped together and defined as a melody. So they're close in pitch and time. Then they are defined as a melody. So I'm going to draw a graph of what this would look like, and I would definitely want you to know and understand and be able to reproduce this graph. Okay, so on the y-axis here I have pitch, right? And so I have high pitch at the top and low pitch at the bottom. And on the y-axis here, I have segregation time. So what I mean by segregation time is how close together the notes are in time. So, and then of course again here I'd have low and high. So if segregation time is low, the notes are really close together, and if segregation time is high, the notes are really far apart. Okay. So what I'm going to do is I'm going to play you two tones, right? And so we'll call the first tone A. And so let's say that A keeps a constant pitch, meaning that it has the exact same pitch every time you hear it. Yeah. Okay. And so the tone, the pitch of A is never changing. You hear the same note just again and again and again. And each time you hear A, in between, you're going to hear another tone called B. And B is going to start off really low, so it's going to be a much lower pitch. It's going to be somewhere down here. And then each time, in between A, you're going to hear A, B, A, B. B is going to climb slightly in pitch. And it's going to get higher and higher, like this. Okay? So, now you have two tones, A and B. A is staying constant in pitch, but B is climbing in pitch. And so what will happen is that here, because the tones are separate in pitch, you'll hear two separate tones. And that'll also happen here. But here, because the tones are close in pitch and time, you'll actually hear one tone that is oscillating. And so we take it for granted when we're listening to music that it's separated, that we can easily distinguish between all of these tones. But I want you to take a moment to remember about how our visual system works. What's happening is that all of these sounds are reverberating out in the environment, and they're creating one complex wave. And it's our job, perceptually, to distinguish the wave. And so one of the ways we do this is in pitch streaming, when things that are close in pitch and time, we actually group them together. And if they're not close in pitch and time, then we consider them separate sounds. And so the final aspect of hearing that I want to talk about today is localization of sound. Which again, as I just mentioned, if all the information that we're getting from our ear is just one complex wave, we need to distinguish where the wave is coming from, much like the retina in the eye has to distinguish where photons of light are coming from. And so it turns out that there are two ways that the auditory system distinguishes sound. And so the first is actually interaural time. Alrighty, so I'm going to spend a moment drawing a picture that I certainly want you to be able to know and reproduce in your notes. And so forgive me, I don't have prodigious drawing skills. Alrighty, so we have a head, and the head is facing forward. And so what we have in front of the head is a speaker. Okay. And so if this speaker is projecting sound, the sound is going to go outward from the speaker in that way, right? And so if the speaker is in front and directly in front of the head, you have a time that the sound will hit both of your ears. And so we'll call this one time one, and this one time two. Right? And notice that if the speaker is directly in front of the head, that the sound will hit both ears at exactly the same time. However, if the speaker is to the side of the head, look what happens. So I have the sound coming this way, and I have the sound coming this way. But now, time one for this ear will be sooner than time one for this ear because the speaker is localized off to the side. And so what happens is that when the sound is localized to our sides, so either a left or the right, the sound wave will hit the ear that it's closer to sooner than the ear that it's further away. Right? And so our auditory system is able to take into account these minuscule differences in time and localize sound to either our left or our right. So the second cue that our auditory system uses is actually interaural intensity. Now, what happens in interaural intensity, and again, I'll draw another picture for you, is your ear is able to calculate the intensity, the amplitude of the sound. And so what it does is it calculates the amplitude for each ear. And so in the auditory system, you might conceptualize this as pressure. So again, if the speaker is in front of the body, right, the pressure of each ear is going to be the same. But if the speaker is to the side, right, the pressure is going to be different. So in this case, the pressure for this ear is going to be greater than the pressure for this ear, right? And so if the sound, again, once again, is localized to the side, you also get information from the intensity of the sound, the pressure, the loudness. And your auditory system is able to calculate that it's slightly louder for your left ear than for your right, and so it can determine where the sound is coming from. Now, for interaural intensity, I want to make a note. This only actually works as a method for localizing sound for high-frequency sounds. So if you remember from our previous classes, a high-frequency sound means that this sound cycles very rapidly. So it might look something like this. And so what happens is as the sound comes along and it hits your big fat head, right, it diminishes the sound on the other side, right, which decreases the pressure. But I want you to look what happens if the sound is of a very low frequency. Okay. Low frequency sounds are actually not blocked by your head. They go around your head. And so they're not blocked, and there aren't any differences in interoral intensity, and so you can't localize low frequency sounds. And so this is why when you set up a new sound system, so if you have a home sound system where you have a subwoofer, this is why it does not matter where you put the subwoofer in the house, because the subwoofer is giving you low frequencies, and so you're not going to be able to localize where it's coming from. But it does matter where you put the tweeters, because the tweeters are high frequency, and those are what's going to give you the localization of sound. So this is all I have for today. I'll see you in lab.